Hello, everyone. Good afternoon. Let's start with this week's lecture, which is on chapter 10 of our digital image processing book. So it's important to note there is only 3 more chapters to finish the book. So let's be brave, have a deep breath, and go on with that. And especially now, this, as I said a few weeks ago, these final chapters they are not more difficult than the initial ones, but the algorithms that are presented in these chapters are a lot more complex. Complex in terms that they all need all of the concepts that have been developed on the first half of this course, and they keep adding other things. So that's why I put these chapters after the little assignment one, because basically if you didn't understand those concepts that the first half of this course, the ones that come now are going to be just impossible to understand. So for today's lecture, I have it's likely over 100 slides. So it may be a 3-hour lecture. So I'll probably have to divide it. Not only I'll divide it into small pieces today, but I might finish it I might finish this subject, which is image segmentation, at the beginning of next week's lecture. So segmentation algorithms is usually based on measuring some discontinuity on the image or some similarity of intensity values. So if we're taking into account discontinuities, then we say that these algorithms they are based on the abrupt changes in intensity data. So you segment the image based on changes in intensity. We're going to see a few edge-based segmentations, which are examples of these algorithms that are based on discontinuity in the image intensities. And on the other hand, you can segment by similarity. Basically, you set a criteria that you're going to judge each pixel with respect to this criteria. And if the pixel falls within this criteria, which we're going to call at the second half of this lecture, they are going to be predicates. So if the pixel that we're analyzing agrees with this criteria, then it's part of a particular region in the image that's going to be segmented into various regions. So as I said, the region-based segmentations are related to these similarity criteria. And in order to segment an image, basically, the basic problem is that I want to assign one level, one intensity level, say 255 white, to the pixels in a particular region. And another level, say 0 or black, to the pixel outside of this region. So I want to segment into foreground pixels representing objects in the image and all kinds of objects, so I can have multiple segmentation, segmenting multiple regions, not only one region. And the background objects, which are things that I'll call just they are not features, they are not regions of interest. I don't want to extract this information, so I basically want to segment. For in a nutshell, I want to get the objects of interest. I want to get one value of intensity, the highest value of intensity, and for things that are not of interest, I want to set the lowest value of intensity or black. So you see, so when to apply one or another, just for you to have an idea. If you should know edge-based segmentation, region-based segmentation is. So you just know so far that edge-based is related to discontinuities, to abrupt discontinuities in the image, and region-based are related to some sort of similarity criteria. Okay, so this you can see here. Let me get a pointer. So you can see here in this image. So you see that there is a sharp change from this part of the image to that part of the image. So there is an abrupt change if you walk from here to there. So with that, I can use the so-called edge-based segmentation algorithms to get the border, the boundary. The boundary is based on intensity discontinuities, and then I get everything that's within the boundary as result of the segmentation. So this is the result of segmenting this image with edge-based methods. Whereas if I try to do the same with this image here, so you see that there's texture here. So the change is not so much abrupt, or better still, there are abrupt changes from this side to this side of the image of this region, but there is also abrupt changes inside of this region. So if I try to do edge-based segmentation on this image, I get this. So basically, it's not a proper segmentation. So in this case, I need to get some sort of similarity criteria. And what is the similarity that I can get from the pixels inside of this region? That's basically texture, right? Texture. So this is a very, the inside of this figure 8 thing here is a very texturized region, whereas outside is a smooth portion of the image. So, and how do I know what texture is? Basically, the standard deviation, right? So, standard deviation is the standard method for mean texture, and I can use this as similarity criterion for the region growing. So basically, when I have a smooth region outside, the smooth region outside will have a standard deviation, right? 0. It's the same. There's no deviation at all. It's the same value. And on this region here, I have non-zero standard deviation. So basically, I do a region growing process by getting pixels that are similar, that have a similar texture, or in terms of standard deviation, that has a similar value of standard deviation. Then I get this segmented region here using region growing, the region-based segmentation. Okay, so let's start from the beginning. So point, line, and edge detection. Basically, the beginning means the edge-based segmentation that's based on discontinuity methods. And we want to use this method to recognize points, lines, and detect point, lines, and edges. So basically, what I want is to detect sharp or local changes in intensity, in image intensities. So what should we use here? Can you have a guess at all? So that's the point where I stop and wait for you to answer, to give a few ideas. We've seen these methods for doing this. Let's say, just put, there's only the two of us. Maybe we'll stay like that. Any ideas? So basically, what we do here is use the derivatives, right? So derivatives are used to detect changes in intensity levels. And the derivatives of a digital functions, they are just finite differences. So basically, if I have an image like that, then remember this, right? We've seen it before the Easter break. And as I said, we're just not just that we are going to use the stuff that we've learned before, and with other concepts as well. So this is imagine that there's this line, this horizontal line, and I'm analyzing every pixel here. So basically, if I look at the intensity levels of that, I have this kind of shape, right? So this kind of shape. So this is a kind of more homogeneous part of image. That's this part here. It's more homogeneous. Getting next to this edge here, so we see a variation, a ramp, a variation of intensity. So the intensity is getting closer to white, and then there is this peak right at the edge here, this peak at the edge. So, and then it comes back, and there's another flat point here, another flat point in the middle here, and then there's another peak here of change, right? And then there is this edge here that's related to this part here, and then at this region we get some homogeneous intensity again. So this is an intensity profile, and this is more or less the intensities that we are getting here. Intensity values. This is going to be 5, 4, 3, 2, 1, and 0. And then there is spike to 6 here, and there is a flat segment. And then here is oh, sorry, this part here is the isolated point. So there is a white point here. There's a white point here. So we have a start here, and then I have a kind of flat intensity that's really white, and then it falls as a ramp to this dark portion of the image. And then here there is this isolated point that is very white, so there's a peak here, and then it goes back to the flat black here, and then it comes here, this portion of a line with a smooth increase here until the middle of the line, and then a smooth decrease here, and then again totally black, and there comes this step here. So these are the intensities, the intensity values. So 5, 5, very white, and then goes down to 4, 3, 2, 1, 0, 0. That's this part of black here, and then there is a pike here. That's the isolated white point. That's right here, right? If you look at the first derivatives of that, we see that there is a change of 1 here. So if it's the first derivative is just 1 subtract, so I subtract 4 and 5, it gives minus 1, and then the other picks 3 to 4, minus 1, and so forth until I get to the portion of reasonably homogeneous intensity where I have 0. The first derivative is 0 here, and then there is this fast change here at one point where the derivatives goes to basically the difference. The derivative goes to positive right, so it changes from black to white very fast, very rapidly. So there is a fast change here, and then it falls negative to black. So it's 6 minus 0. That gets the first derivative. Then it's 0 minus 6. It gives you a minus 6 of derivative. And there is a flat segment here, with this flat segment 0 with no change at all. And then you see, sorry, that's here. And then you see the line coming here where you get intensity changing, the derivative changing slowly, and then changing the direction of the derivatives. So what can we get from this? And then here at the ramp you have a fast change, and then right at the edge, and then there is this homogeneous where the derivative is 0. So basically, from the first derivative, we can recognize where a very fast discontinuity is in the exact position in these intensity profiles. So if you get this point here, basically, if I want to locate this point here, imagine that you only have this this horizontal profile. Then I get I just look at this when there is a rapid change from positive to negative here on the first derivatives. If I want to locate regions of constant intensities, I just look for 0, where the first derivative is 0. If I want to locate a line, then I can see something like that it smoothly changes from one direction and smoothly changes to the other direction. If I change to find a step, I just look for an abrupt change from something that's constant before and something that's constant after. So basically that. And the second derivative is very informative as well. So the second derivative informs the exact point where the change happened. So here, when it changes from constant to the ramp, That's this point here. That's the second derivatives as the second derivative gives you a value. Whereas constant change, second derivatives doesn't see it. It sees as it's just constant change, right? Second derivatives, the derivatives, what they picked out is just changing. Whereas again, so this has a change of negative, so it changes from white to black, and then this sudden change at this point here, at the end of the ramp, when this went from white to black, there is +1, so you see the direction of change first from white to black, and then you changed here from -1 to 0, so that's 0 minus -1, that gives you 1, so it gives you the direction of change. And whenever there's this abrupt change or the isolated point, so you have a very sharp increase here, so very sharp from 6 to -12 and to 6. So the main idea of using the first and second order derivative is to guide you, is to locate these points where there's basically to locate points, edges, and lines. But if we use only the first derivatives for generating the edges, you can see that whenever there is a change here defining an edge or a line, the first derivatives produce thick edges. So if I want to reproduce this image as the image of the changes of the edges and points, we're going to see that this edge here will be quite thick. The edge that's separating this region from that region will be quite thick. Whereas if I use the second derivatives, that will be just a line here. Okay? Second order thin edges, as I said, would be just line. Isolated point for the second order derivatives produces a stronger response, and it's more sensitive to sharp changes. Thus, we can use the second derivatives to enhance fine details, including thin lines, point, and unfortunately also noise. So the second derivative is quite sensitive to noise. The line is too fine, then you're going to have a strong response for the second derivative, as I've already said. Ramp and step, the second order derivative will have opposite signs, so we'll have opposite signs here indicating the start of the ramp and the end of the ramp, and also the step here, the start of the change and the end of the change. So you see that the step is a very rapid change here, very fast change here. So basically, you just look at the second order derivatives where the opposite signs are. This gives a double edge effect. If you think that you're going to have one edge here at 7 and another edge at -7, so you have this double edge effect. And light to dark, we are going to have the change from positive to negative on the second derivative. And dark to light, you're going to see a change from negative to positive. And exam question, if we had an exam for the second part of the course, how do we obtain the first and second derivatives of a digital image? So there's another point where I stop and ask the questions to everybody. You probably remember that. We've just done the assignment 1. If you don't remember this, it's because the assignment 1 was badly made. I think I put some questions about gradients for that. We use spatial convolution at every pixel location. Remember spatial convolution, right? You've done that on the assignment 1. You had to do it by hand. So it's basically you get a kernel representing the first derivative, right, or the second derivative, and we just convolve this kernel over the image, right? That's how we obtain the first and second derivatives. So for point detection, we use the second order derivative. We can use the Laplacian kernel for it, one of the discriminations of the Laplacian kernel. And the point will be detected at x and y, at the point where the kernel is centered. if the absolute of the response of the filter exceeds a given threshold. So basically, I just pass a Laplacian kernel and threshold on the kernel results to get a point. And we label this point as 1, and all others are as 0. So using this kind of idea, right? So if the result of the Laplacian is greater than a particular threshold, I say that this pixel will receive a value 1 or 225, depending on how you are labeling these pixels, and the other pixels I'll just put the value 0. Okay, so point has been detected at x or y if you get the filter's absolute value is greater than a threshold. So again, it is Laplacian kernel here. Do you remember this Laplacian kernel? And passing this kernel here. So that's on this X-ray image of a turbine blade. And then you want to locate the some defect. So this is a porosity manifested by a single black pixel here. This is the result of convolving the kernel with the image, and then we just apply a thresholding method here. So we just get the maximum points of the Laplacian. So 10.15 equation 10.15 is this equation here, right? Just this equation. So basically, the result is a single point. I honestly can't see this point as enhanced in this image. Maybe on the book it's more visible, but well, that's the way you do. And there's always the question. That's the simplest way, actually, of locating a point. There's a number of other points. There's always the question. It's always the case with these algorithms: is how the hell would I know the threshold? Well. So we call these methods as intelligent, but they are not so intelligent. They just do brute force. The intelligence is still human, and you're gonna see from these more complex algorithms that we'll see from today and till the end of this course. The parameter setting is one of the main challenges of all of these methods. So basically, we need still a lot of human intelligence on that. I just look at the printed book, and I can see clearly this point here on the image, right? And that's the point we've discussed that, right? So how you represent it. So there's a certain resolution in this in the way that the image has been printed. There's another kind of resolution in the way that these images have been provided. And my monitor has a kind of resolution, and your monitor has another resolution. So basically, we can't see it, but on the way that's in the printed version of the book, I can clearly see the defect at somewhere around here, right? Just a whiter spot. Okay, so line detection. So this is the end of a very basic algorithm for detecting points. Just pass the Laplacian kernel, get the absolute values of the resulting image, of the result of passing the Laplacian kernel on the image, and then threshold. The trouble is finding a threshold. Line detection. So line detection, as we've seen, the second order derivative produces a stronger filter response and thinner lines than the first order derivatives. We use again then the Laplacian kernel, right? But the problem here is that we have to take into account that the Laplacian has negative values. So we have to set these values into some sort of scale. So we can see on figure B here that that if the mid gray is points where the Laplacian is 0, mid gray is this, lighter gray is where the Laplacian is greater than 0, and darker gray is the points where the Laplacian is less than 0. So we can detect this edge, right? So we just see where there is this strong variation between darker gray and whiter gray, that's the edge. That's the line that I want to detect. But I can't handle negative values because we can't basically. The images are defined from values 0 to 255. You can also decide from 0 to 1. It's the same thing, but there's no definition of a negative intensity value. That would be very odd. That would be a very odd thing to do. So ideas to eliminate negative values, we could get the absolute value. We could get the absolute value of the Laplacian, as we've done on the point detection algorithm. But this, as we see, instead of getting a line, a very nice sharp line, we're going to have a very thick line, because if you get the absolute values, then we're gonna sum this portion, the dark portion with the white portion. This is going to become one very thick line. It's not what we want. So basically, what a solution is to threshold only on the positive values of the Laplacian. So if you see here, this is the original image. That's the result of passing the Laplacian filter. If I just use the absolute values of the Laplacian, then I get these very strong responses, very strong lines, which may be what you do, what you want. But sometimes you want the most precise version of the edges that you have from the original image. And if you get only the positive values of the Laplacian and threshold on them, then I see this very nice kind of line. So that's how we detect lines. So if I give you this picture here and say, oh, give me all of the lines, you can give me this picture here, where that's segmented, right? So we just want these pixels will have one label, that's 1 or 255. But let's label the pixels 0 and 1, where 1 is foreground, 0 is background. So these pixels here that will all receive a label 1, and all the rest will have a label 0. That's a segmented image, right? So you know exactly where the lines are of this circuit. Okay, so I can also use kernels that are specialized for various line directions, right? So I have this kernel here that's basically a detector of horizontal lines. So it's going to have a sharper result when I have an horizontal line. This pixel here will find lines that are 45 degrees. These pixels here will get lines that are vertical. In this kernel here, will get lines that are also minus 45 degrees, right? So you see that this is the negative of that. This is rotated 180 degrees. So that's these. In order to detect lines in specified directions. So suppose an image is filtered with these four kernels, one at a time. So I'll filter this, or pick an image with this kernel, then with this kernel, and then with this kernel, then with this kernel. And at a given point, you have the response of kernel K is greater than the response of all the other kernels that are different from K. So basically, I associate that point with a line in the direction of the kernel K. Right. So basically, so I'll pass the kernels and associate the direction of the line to those that to the appropriate kernel, to the related kernel, to the kernel related to that direction, but the one that had the strongest response. So if we're to detect all the lines in the direction defined by a kernel, run the kernel through this line and get the kernel, the appropriate direction, the kernel related to the direction that you want to find, run it through the image and threshold on the absolute value of the result obtained. So think we've done something similar to that when we were discussing gradients, right? There was a question at the end of one of the lectures and said, oh, so okay, so now I have this very nice image that's the gradient image of the original the input picture. How, if I want to get all of the vertical lines, what do you do? And someone said, well, you just take the threshold, you just threshold on the values of the absolute values of that given kernel that we use to segment the image. So that's it. So just pass the kernel and use the absolute values and threshold on that. So this is the result then of detecting lines in specified directions with the same image here. There's the image of a wire bond template. This is the result of processing this image with a 45 degrees line detector kernel, basically with this kernel. So I've got this is the result of getting this image and passing this kernel here, right? So this is just a zoomed view of the top left, zoomed view of this part here. This is the zoomed view of the there is where's the image E is this one. So this is the segmented image where you had all of the negative values set to 0, and I just got the positive values, and then I use a threshold. So if I want to detect, you know that this kernel is going to have the highest values on the 45-degree lines. So I just threshold this image here. That's the result of this kernel with the background picture set to 0, and I threshold to a particular value. And I have only what? I have only lines that are 45 degrees. Okay, so let's look with how to detect lines. Now let's see how to detect edges. There are various types of edges that we should take into account. The step edge, that is the ideal type, where you have a fast, immediate change, so from black to white. So I have a step when the change occurs. It never happens in practice. What we usually have is something like this, where I have a ramp edge. It basically can be understood as a step edge plus some Gaussian noise around this region, right? And roof edges, when I have edges that vary like this, basically these are models of lines to regions. These are basically what we've been doing the previous slides. So in a real image, we can basically find all sorts of edges. There are quasi-step edges here. So if you look at this portion here, and this is a line, right? This is a line. This is a line. The portion of this skull that gets outside of this image. So it has this kind of rooftop edge, and this is a smooth edge. That's called a ramp edge, right? Now, how do I find an edge? We're not very creative. Use the derivatives. It's the derivatives of an edge. So basically, you get usually the edges are like this, and the results of the first derivative of that will be constant for constant portion of the image. Then we'll have a rapid change here at where the ramp starts, and then a rapid change here where the ramp finishes. And if obviously this is a very smooth ramp, so with a very smooth ramp, the rate of changes will be constant. So the gradient will have the first derivative will have a smooth shape here. And if we look at the second derivative, we're going to see that here changes from 0 to 1 was a positive change, and then here at this edge here, this other edge at the end of the ramp, it changes from from 1 to 0, and there was this was a negative second derivative. So the point of the zero crossing is the very middle of the edge of this edge that I want to detect. Okay, so basically the first derivative will be positive at the onset of the ramp and 0 where there is constant intensity. The second derivative will be positive at the beginning and negative at the end, and 0 at the point of the ramp and 0 at the constant intensities. So which one should we use? So basically what we're going to do is to use the magnitude of the first derivative to detect the existence, to detect the presence of an edge. And of course, as all this area does, it's not it's the absolute magnitude above a particular threshold. So we're going to use we run a first derivative kernel, a gradient kernel, threshold the resulting image, and then basically we're going to get very strong changes, so pointing to potential positions of these edges. And we're going to use the sign of the second derivative to detect whether an edge pixel lies on the dark or the light side of the edge. And the second derivative zero crossings to locate the exact center of the edges. Okay, so that's all what there is to the detection of points, lines, and edges. So what happens in the presence of noise? Obviously, well, noise makes everything more difficult. So if I have an image like this, so this is the image, so this is the variation, and this is the first derivative, and this is the second derivative. So this first bit here is without any noise. So I see exactly the theoretical results that we've seen before, that we've seen here, or better still. That's it. It's far back. Yeah. So basically, what we've seen here on this profile, without noise, but when we have noise in these kinds of images, so basically, if I have just a little bit of noise, that's a Gaussian noise with zero mean and standard deviations. The initial one is a zero standard deviation, so I don't have any noise. So 0.1, then I get this sort of shape here. I can still see the first derivative. Whereas the second derivative here, well, it's pronounced here. Yeah, we can see it, but it becomes a bit harder to see. With a standard deviation of 1.0, then I get this mess here, right? So it still can see some sort of changes if we really believe that there is a change here, but definitely I can't say anything about the second derivative. And if I have 10.0 standard deviations of intensity levels for the Gaussian noise, then I don't have any. I don't see any second derivatives or first derivatives, but it's still I can see the shape here, so I can see that there is a step here, but I can't use the derivatives in this case. So what shall we do to solve this problem with the knowledge that you had so far? There's an easy fix. But before we talk about the easy fix, so the second, just to summarize, the second derivatives are useless for noisy images. So what can we do? You do smoothing. You do smoothing. So you pass a Gaussian filter and you smooth it out. Remember when we're talking about smoothing that that I said, well, look, why would I want to blur the image? If by saying that I'm going to reconstruct the image by blurring. So blurring is just a process. It's just one step in a process. So so basically, if I blur this image here, we're going to get something that's closer to this, where I can have a pronounced first derivative and somehow a second derivative still showing in the profile. So the typical steps for edge detection would be first image smoothing for noise reduction. Noise reduction, you know everything about it, right? So you had to write an essay in the assignment 1 related to noise reduction, right? What kind of noise? What kind of noise models are there, and how can we fix these noise models, right? You know everything about that. So now you just apply your knowledge. So first, find what kind of noise you have, apply the appropriate filter for it. Then use detection of edge points, find the candidate points by using the first derivative, then the edge localization, select from the candidate points only the edge points by using the second derivative. So basically what we do for edge detection, we use the gradient for finding where the changes are. We threshold on the gradient magnitude to get only the very best changes, only the most pronounced changes. And we can use the gradient direction. Look, the gradient directions to find the direction of the edge. How would you know the direction of the edge of the gradient? You know that the edge will be orthogonal to the direction of the gradient, right? So if we have an image like this, this dark gray is background, and while white is higher intensity. The gradient always points at the direction of the change. It's the direction of the change. So orthogonal to it is exactly the edge that's changing. The very boundary between one particular behavior of intensity levels to the other behavior intensity levels. We can use the direction of the gradient that's calculated using the arc tangent of the gradient, and that's it. So we have the direction of maximum change, and the orthogonal to the direction of maximum change is the edge direction. So we know everything about the edges, about finding edges now. In gradient operators, we all know, you've studied that. Just to remember, so we have all of these, we've seen all of these, Roberts, Previtz, and Sobel, not sober. I am sober today, but the gradient is Sobel operator. Any of the pairs of these are convolved with the image to obtain the components of the x components and the y components of the gradient. G here refers to the gradient, right? So this is this gives the x component of the gradient. This gives the y component of the gradient. If you want a better solution than the Roberts gradient, use the Previtz gradient. If you want an even better, you use the Sobel. That's slightly more robust to noise. Use this to estimate the edge strength and direction using the magnitude and the direction of the gradient. And we get the strongest response of vertical and horizontal edges for finding what? For finding our edges. Okay, so there are other kernels. So these people are crazy about kernels. They only think about kernels. There's this Kirsch compass kernels. I think we may have seen some version of it. So basically, this Kirsch, it was going to give you the strongest response in each direction. So this kernel here will give you the strongest response in the north direction. And I think north is pointed here to the right. From northwest, from west, from southwest, south, southeast, east, and northeast, and so forth, right? So edge, magnitude, and direction, we basically convolve the image with all 8 kernels. The magnitude at that point will be the response of the kernel that gives the strongest convolution value at that point. The edge angle at that point is the direction associated with that kernel. So that's basically the same thing as we've done here, but these 2 kernels are only going to give the x and y coordinates of the gradient. If you use these compass kernels, they are going to give the 8 directions. So you have a more precise, well-defined variety of edges, but of course you have to convolve with 1, 2, 3, 4, 8 kernels. That's computationally more involving. That's why I've never seen any application of the Kirsch compass kernels, but I've seen loads of applications of Sobol. Sobol is very famous. It's a very famous. I think it's the key, is the most important of these gradient kernels is the Sobol. Okay, so let's see some results. So this is an image, quite big image of size 835 to 1001 to 11,014 pixels, with intensity values ranging on from 0 and 1, just to facilitate what we're doing. So the image B gives you the X component of the gradient kernel, basically gives you the very pronounced response on pixels that lie on horizontal lines, using the Sobol kernel, using this. And this image C then is the vertical. It gives the strongest response to pixels that are located on the vertical lines. So by combining one with the other, I have this very nice image. Is it good enough for segmentation? What do you think? No, it's not good enough. It's not good enough. I have noise here, so this is something that it should not be here, because this part of this pixels here do not lie on any horizontal or vertical line. Okay, so this is basically it's kind of, it depends on what you want to do. You want to just enhance the image, or you want to really extract the edges. So that you should see. But of course, there is the simple solution for this problem here is you smooth the image first. Too much detail of this, it's basically, in terms of gradient, that's noise. So what do? You smooth the image, and then you apply the same principles. You apply the X component of the gradient, that's the result. You apply the Y component of the gradient, that's the result. Summing one with the other, get this very nice kind of. Oh, this is nice. That's definitely. And there's still some noise here, but it's definitely a lot better than this thing. Definitely a lot better than this thing. So what we see as a result is mainly principal edges in the image. Not much contribution from bricks. There's still some contribution from bricks here. So now we can combine the gradients with thresholding. So basically, to extract the edges, I just get this image here in threshold on with an appropriate threshold that's going to extract these lines. That's the result of thresholding this image. This image is the gradient of this image, using what did he use for that? I think he used the Kirsch kernel, the one that finds every single direction, right? So this is a very nice segmented image. So we can find edges. So why do we need that? So if we want to recognize, if you're doing processing for the RoboSoccer domain, for instance, you're going to use this kind of filters to find the posts, the goalposts. So if we're doing processing for an autonomous vehicles, one important thing that the autonomous vehicles have to observe is the lanes, right? So with the lane paintings on the streets. So you can use this kind of methods to segment the lane straight lines, right? So find where the lanes are. Of course, today we have better methods for doing this, but these methods for combining gradient with thresholding are still used as a first level before applying the more advanced methods. That's why I'm teaching you all of these very foundational methods. They are used all the time. I don't use this whole image. That's too messy. If I don't give a system this whole image. That's too messy. So I'll give already some indications of where the edges are, and in particular for industrial applications. In industrial applications where you have we're going to talk a little bit more about industrial applications. When you have controlled lights, controlled environment, you don't want to use a neural network that's going to take ages to train, and it's going to be bound to errors and all sorts of other stuff. Although it's very powerful for problems that are uncontrolled. So if you're in a controlled environment, these are the methods that you're going to apply. You're going to apply gradients and thresholding to find edges or to find points. Okay. Right. As I said, there are more advanced techniques for edge detection. So the previous techniques we filtered with kernels that disregard the edge characteristics or noise. So more advanced methods take this into account. And one of the oh no. How can I get rid of this? Okay. So one of the methods is the smart Hildreth edge detector, which, to tell you the truth, I almost skipped from the book. It's a nice method, but I haven't seen people using it very much. But I decided to keep it there because there is one key concept in image processing in computer vision. One key concept. Let me just see if there are questions. Okay, no questions. So there's one key concept that we're going to see in a minute. So main ideas: intensity changes are not independent of image scale. So that's what we want to get from this. That's the main idea behind the smart Hildreth edge detector. Intensity changes are not independent of image scale. The detection requires operators of different sizes. A sudden intensity change gives rise to a peak in the first derivative. We've seen that, right? Or equivalently a zero crossing on the second derivative. Thus, I don't want to keep doing all of these steps. That was the central idea of Mark Hildreth. We should find a differential operator for the first and second derivatives at every point of the image. That does all the trick. That does all the trick. That does all the job in one go, in one pass through the image. And also should be tuned to act at any desirable scale. So we should have large operators for blurry edges, small operators to detect sharply focused fine details. So which operator we're going to get? That's the key idea. That's the key idea that I've seen an infinite number of times applied in various computer vision algorithms. That is the so-called Laplacian of Gaussian, the LOG, the Laplacian of Gaussian. So we all know that's the formula of the Gaussian in 2 dimensions, right? X and Y, because I want to apply it into a 2-dimensional image. So I need to pass a 2-dimensional Gaussian filter. And the Laplacian of Gaussian is this operator here. It's just the Laplacian of this formula here that gives this formula here. That's the LOG, or the Laplacian of the Gaussian. That has this very nice shape of a Mexican hat. It's also called the Mexican hat operator. right? And and because of this shape here, it has the best of both worlds, as we were wondering. It has a differential operator for the first and second derivatives at every point of the image. It has the zero crossing of the second derivative. It has everything that we want. And on what? On a single kernel. On a single kernel. Where did I get this kernel from? That's just a discretization of this. It's just a discretization of the Laplacian of Gaussian. And I want to stress that the Laplacian of Gaussians appear in many places, with different sizes. We are going to see in one particular method, I think, next week, that's SIFT, the scale invariant feature detector. The first step is using a Laplacian of Gaussian. Just to pin down, so that's just the Laplacian of a bidimensional Gaussian that has this shape of a hat, has this kernel, and that's all what there is to that. So what are the main ideas behind this very nice operator? So the Gaussian part of the operator, what is the Gaussian part? That's it. There's still a little Gaussian here, you see? The operator itself, that's the beauty of the Gaussian. Whatever you do with a Gaussian, you still have a Gaussian. That's amazing. That's unbelievable. You have a Gaussian here. So when you pass this operator through the image, you're already smoothing. But you also have this. So this is what? This is the derivative. So I have a smoothing operator and a derivative, both combined into a single operator. That's what it says. So the Gaussian part of the operator blurs the image, reducing the intensity of structures, including noise. And the Gaussian function is moving both spatial and frequency domains, so it's less likely to introduce artifacts. The Laplacian is invariant to version, and that's a characteristic of the human visual system, and responds equally to changes in intensity in any kernel direction. It's actually symmetric, not asymmetric. It's symmetric. There are many symmetries. There's a symmetry here, a symmetry here, a symmetry here, a symmetry here. So basically, I don't need to bother passing all of these filters in many directions. This is all there. It's beautiful, isn't it? It's beautiful. Okay, so it's all here, everywhere. It avoids having to use multiple kernels to calculate the strongest response at any point in the image. Okay, so that's the algorithm is pretty simple. So basically, you filter the input image with a Gaussian of a certain size, low-pass kernel filter, obtained by sampling the Gaussian. Compute the Laplacian of the image resulting from step 1. The Laplacian kernel. Find the zero crossings of the image. And the way to find the zero crossings at a particular point, you use a 3x3 neighborhood centered at every point. And a zero crossing at P means that at least two of its opposing to the center of this neighborhood, must differ, right? So a zero crossing at a point P means that at least two of its opposing neighboring pixels must differ. One will be positive. Compare the difference against the threshold, and you get this, right? So same image. This is the step 1. This is the blurring when we pass the Gaussian filter, and this is when you get the gradient. And this when I use the zero crossing and thresholding up to a certain degree, right? These are the zero crossings, and this is the result of thresholding, with a threshold equals to 4% of the maximum value of the image in B. So that's quite a neat kind of segmentation. Of course, there are gaps, but then I'll have to, if I want to reconstruct the exact case, I'll have to reconstruct the for every section of this, I'll have to reconstruct the the line equation, and then I can just build the image again. I guess that's good for a good break. Stop the recording now, and just to get this lecture in 2 parts, or maybe 3 parts, and so I'll meet you in a bit.